So continuing our introduction to ring theory, I have a couple of new definitions. So here's a definition. Let phi be a ring homomorphism. I'm going to define the kernel of the ring homomorphism. It's going to be very reminiscent of the kernel of a group homomorphism. So the kernel of phi is abbreviated ker phi. That's just the set of everything in your ring that phi sends to 0. That's the 0 in S. So this 0 here is the additive identity in the ring S. Okay, so let's see some examples. The kernel of the ring homomorphism that sends integers to integers mod n, defined by phi of A is A mod n, is everything that the homomorphism sends to 0 in Zn. So every multiple of n. I could write that down as nz. So n times any integer is the kernel of this homomorphism. All right, let's do another example. Let's do the evaluation homomorphism. So let's look at the kernel of the evaluation homomorphism phi. It's going to send polynomials with real coefficients to real numbers. Let's say I'm going to define it by phi of a polynomial is P2. So I'm going to plug in 2 wherever I see an x into the polynomial, sending my polynomial to a real number. This is the set, everything of the form x minus 2 times q of x, where q of x is a polynomial. I want to get out 0 to be an element in the kernel under this homomorphism. So if I plug in 2 into a polynomial of this form, I'm guaranteed to get out 0. So that's the kernel of the evaluation homomorphism. All right, so that's the definition of kernel. The other definition I wanted to get across right now was the definition of an ideal. So an ideal of R is a ring, is a subring I such that Ri, that means you take an element R in the ring, multiply every element in I. This has to be a subset of I, and your ring may not be commutative, so order of multiplication might matter. I'm going to also demand that IR is a subset of I, and this has to be true for all R in the ring. So this is the definition of an ideal. Let's see examples. Well, what about this subring? It turns out that NZ is an ideal of Z. It's a subring. It's a subring. It's closed under addition, it's closed under multiplication, and it has additive inverses. And it also satisfies this condition. Why? Well, if you take any r you want that's an integer, and you multiply by the set nz, these are all multiples of n, you're still going to get back multiples of n. So if you take a multiple of n, multiply by r, you still get a multiple of n. So that verifies the first condition. And in this example, the ring is commutative. I could switch r and put it on the right. Doesn't matter. Multiplication of integers is commutative, so that actually verifies both conditions. So I have an ideal of z. Let's do another example. Well, here I have another subring. Let's look at the kernel of the evaluation homomorphism. Let's look at this set. So let's say I is everything of the form x minus 2, q of x, where q of x is a polynomial with real coefficients. This is an ideal. Why is that? Well, first of all, it's a subring. It's closed under addition. You add two things of this form together, you get back something of this form. It has additive inverses, and it's closed under multiplication. You could verify that if it's not clear to you right away. But additionally, it satisfies these two properties. If I take any polynomial r of x and I multiply everything in I by r of x, I get back something in I. Why is that? All I'm saying with this condition is that if you do r of x times something of this form, then you get back something of this form. Multiplication of polynomials over the reals is commutative, so you can rearrange terms and get this. Now you're back in I. Okay. I defined kernel. I had two examples. The kernels both happen to be ideals. That's a general theorem. So we'll end this video by stating and proving the theorem. Let phi go from R to S be a ring homomorphism. All right. Then the kernel of phi is an ideal. Ideals are going to take the role of normal subgroups. So ideals are subrings that have a property that's not dissimilar to normal subgroups. If I was in group theory and I had a group homomorphism, the kernel of a group homomorphism would be a normal subgroup. So hopefully you're seeing a few analogies to group theory. Okay, what's the proof? I have to show these two conditions hold. Well, I guess first, technically, I'd have to show I have a subring. So the kernel, is it a subring? Let's take R1, R2, and R3 in the kernel. Then phi of R1 plus R2, R3 is equal to phi of R1 plus phi of R2, phi of R3. R1, R2, and R3 are in the kernel, so that means every term here is 0, implying R1 plus R2, R3 is back in the kernel. I kind of showed in one fell swoop that this subset, the kernel, is closed under addition and multiplication. It's because I could take R3 to be 1, for example. My definition of ring says it has unity. I could take this to be the multiplicative identity if I want. Then I'm showing that phi is the kernel is closed under addition. Or I could take R1 to be 0, and then I'm showing phi is closed under multiplication. So I showed closure under addition and multiplication kind of in one step here. Additionally, to be an ideal, I have to show that additive inverses are in the kernel. So if R1 is in the kernel, then phi of negative R1, well, that's the same as phi of negative 1 times R1, which is phi of negative 1, phi of R1, which is 0. So I also have additive inverses in the kernel. This shows I have a subring. Next, to prove that I have an ideal, I need to show that these two properties hold. So how do you do that? I'm going to take an element A in the ring arbitrary. So take an element in R arbitrary and take B in the kernel. Then phi of AB is phi of A, phi of B. Phi of B is in the kernel. B is in the kernel, so phi of B is 0. So this is 0. This gives me phi of A times 0, which I think we proved in a previous video. Anything times 0 is 0. This proves that A times B is in the kernel of phi. What this shows is that A times the kernel of phi is a subset of the kernel of phi. Why? I took an element A, B in this set, and I showed it was in this set. So I showed containment. Therefore, this first property of the definition of ideal is satisfied. The second property is similar. I don't think I want to show it. So the condition, when I put A on the right being a subset, is similar. So I claim that I am done. The kernel of a ring homomorphism is an ideal.